Hello everyone, this is the video lecture of section 6.5. Okay, section 6.5 is average value of a function. Okay, let's see, where is the... Alright, 6.5. So, if you have a finite number of data, let's say y1, y2, y3, yn. The average value of these data, or mean of these data sets, would be just add all these data up and divide it by number of data. Okay, so that was easy. Now, what if your data is not made of just finite number of measurements, but infinite number of excuse me, data? Let's say excuse me, oh. So you have some quantity represented by a function of f of x from a to b. Now, how can we consider what? So we want to talk about the average value of this function. Okay, let's say that was some weight, whatever the quantity is. It's a function of x. All right. So you have infinitely many data. In that case, how can we make sense out of average of this quantity y, average value of y, or average value of function f? Right? Now, so here, f is continuous. It is continuous function on a to b. All right. So, how can you define f average on this interval? The question is, how can you define? Now, let's say if you don't have any idea what to do with this, then you might approach this way. Let's think about small subintervals. Okay? Let's say, as usual, delta x, the size of this subinterval is b minus a divided by n. N equal size of subinterval. Okay, this is x1, x2, xi minus 1, xi. For each subinterval, because it is continuous, if delta x is small, then on each subinterval, your function values are very close to constant. Doesn't vary much. So you just consider x1 star, any, over here, xi star, some, sample point from each subinterval. By the way, xi is a plus I delta x, usually. So, instead of thinking about this is continuous function, we think about the data over here, or each xi stars, alright? Over here. So we think about these n datas, right? This is x1 star f xi star. So our approach here is f average will be pretty close to, it should be close to x1 star plus f x2 star divided by n. See, if n is very large, many subintervals, on each subinterval you just evaluate function value somewhere. Because when delta is very small, no matter where you choose xi star, function value will be more or less same. So we just average out those sample point function values. If n is large, this should be very close to the whatever the average value we want to define, right? Now this one, you can write it, look at this, b 1 over b minus a, f of x I x1 star, f of x2 star, f of x n star, and b minus a over n. See? This b minus a, this b minus a cancel each other, and 1 over n over here. So this is exactly the same thing. Now I can write this one as 1 over b minus a, sigma from 1 through n, f of xi star. This is nothing but delta x, isn't it? Alright? So this is your average of function value. Should be very close to this. Larger the n, the better this approximation. So we take the limit. So we want this to be limit as n goes to infinity of this value. Okay, this is nothing but limit of Riemann sum. It's definitely integral. 1 over b minus a times a to b f of x dx. That's how we define average value of a function. Okay? Definite integral of f of x from a to b divided by its length of the interval. Okay? So this is a very nice approach. Okay? All right. Now, one remark. Your AB f of x dx is f average times size of the interval. So, if you're like this, let's say, something like this. This is the area of the region under this graph. This area, A to B. Now, let's say your average value is somewhere f average somewhere. So if I draw the line, this is b minus a times this one is the area of this rectangle, isn't it? So that means average value of the function is the height of the rectangle whose area from A to B is same as the area of the region under the graph of f of x. That's the meaning of this rewritten version of definition of average function, average value of function, right? So average value of the function is a constant value such that if you keep that constant value on that interval from A to B, then the net effect, accumulation of that, so area of that constant function graph must be seen as definite integral of f of x. the area of the region under the f of x. Of course, we are just assuming that f of x is all greater than equal to 0, but this thing works whether f of x is positive or negative. Alright? So, that is the concept of average value. This is the definition. So, for example 1. Find the average value of the function x squared on 1 to 3. Oh, negative 1 to 3. Well, just the definition. Average value on that interval. Alright? 1 over b, which is 3, minus a, which is negative. The size of the interval. 1 over size of the interval is 1 over 4, from negative 1 to 3. F of x, which is x squared, dx. So what is this? This is 1 over 4. This is 1/3, x to the third, from negative 1 to 3. 1 over 12. 3/27 minus of negative 1. 28 over 12. 4 cancels. 7 over 3. Okay? So when you have a graph like this, it's just like 2.33. Alright? So if you draw 2.33, you keep the same area as on the graph. Okay? Alright. Now let's review mean value theorem here. Mean value theorem. Review. Mean value theorem was this. If f is continuous on a to b and differentiable on this open interval, then there exists some c between a and b such that f prime of c equals f of b minus f of a over b minus c. Okay, let me check the video. Okay, so graphically that means that if you have a function like this from a to b, you know, there is some point C where, so this is the slope of this secant, and you have a point where tangent slope of the tangent line is same as slope of the secant. That means parallel, right? Parallel. That's the point we are talking about. You could have more than one, but this theorem says that as far as your function is continuous and differentiable inside, there must be at least one such point C. Now we can have mean value theorem for integrals. Mean value theorem for integral. That says that theorem, THM theorem, if f is continuous on AB, it's no longer has to be differentiable, just continuous is enough. Then there exists C somewhere between A and B such that your f of C equals the average value. That is okay. If your function f is continuous, then your average value will be appearing as a function value somewhere here. All right? F of c will be your function value. F of c will be, so your horizontal line from y equals f average value will be intersecting the graph. Okay? It makes sense because your function is all continuous, that means connected. Somewhere is above, somewhere is smaller than average, that has cut through somewhere. Now, how do you prove this? Well, this is actually direct corollary of the mean value theorem, original version of mean value theorem. Okay? Proof. Let capital F of x be an antiderivative of lowercase f of x, i.e. your f prime of x equals f of x. Okay? Then your 1 over b minus a from a to b f of x dx is, look at this, 1 over b minus a. This is using fundamental theorem of calculus, capital F of b minus capital F of a. Right? Now, capital F is antiderivative of this. Okay? That means your f is continuous on a to b and differentiable on a to b. Why? Because by definition it's differentiable. Now we can find any antiderivative of any continuous function, because one way to have that is a to x f of t dt. From the fundamental theorem of calculus, this derivative is f of x. And obviously, because it is differentiable, so it is continuous. Alright? So anyway, so this part is the first form of the fundamental theorem of calculus, or evaluation theorem. Now, let's rewrite. Because capital F now satisfies this hypothesis of original mean value theorem, by original mean value theorem, because capital F is continuous on the interval, differential inside, therefore there must exist some c value between a and b such that your capital F prime of c equals this value. I.e., what is capital F prime of c? Lowercase f. What was this expression? That was 1 over. This is it. We must have such c value between a and b. There must be a function value point where function value is same as the average value, as long as f lowercase f is continuous. Okay? In example 2, let f of x be x squared on -1 to 3, just like example 1. Okay? Then find c, which is guaranteed. Guaranteed by mean value theorem for integrals. Okay? So, in example 1, f average value, that one was what? 7 over 3. Now we want this to be equal to f of c, right? F of c equal to average value, right? And this is c squared. Therefore, c must be square root of 7 over 3 or negative square root of 7 over 3. In this interval, this is not in that interval, only this one. So, the c value guaranteed by this mean value theorem for integrals, for this case, x squared function on interval minus 1 through 3, the c value will be square root of 7 over 3. Okay? Alright, of course, if you want, you can write it. We no longer care about rationalizing denominator in calculus. Alright, that was a very short section, section 6.5. This is the end of section 6.5. Thank you. See you next time.